Hello everyone. Today we'll be starting with the topic electric field. We'll try to understand what electric field is. So to understand electric field, first of all we take a positive charge at some point. So here we take a positive charge plus Q. Now if I bring about any test charge. So a test charge is a charge which is very small tending to zero. It has to be very small. So here we bring about a test charge nearby this charge q. So this is our test charge which is represented by q naught. A test charge is necessarily positive and it's very small. So now this test charge q naught, it experiences a force due to this charge q, since there are electrostatic forces of attraction and repulsion between two charges. So here since the two charges they are placed a few distance apart, so therefore they exert a force on each other. So this charge plus q, it exerts a force on this charge q naught. Now to understand how one charge is able to apply a force on the other, as we can see that there is no contact between them. So to understand how the two charges are applying force on each other, there are two methods which were discussed. Either there are some exchange of particles, that is, you can say that there is some bonding by the exchange of particles. The other concept is the field model. So this field model, it explains how the force is experienced by this test charge. According to the field model, this charge plus q, it creates a space around it. The space around it is an electrified space. It is an affected space by the presence of this charge. So this space around the charge q, where its effect can be experienced, is called as an electric field. So wherever at any point in this, suppose I placed it over here, I place it here, so this test charge will experience a force due to this plus q. Now suppose I place it very far off over here, so here the force experienced by this charge q naught may not be there, as it's so far that the electric field of this charge is not over there. It cannot experience the force due to it. So electric field is the space around a charge where its effect can be experienced. So here the everywhere for this charge we have taken a spherical volume in which wherever we are placing the charge, it experiences a force. So the electric field intensity over here is given by electric field intensity E is given as the force experienced by the test charge per unit test charge. So electric field is a vector quantity. It is in the direction of the force experienced by the test charge. So here the test charge q naught, it experiences a force. So force per unit test charge gives us the electric field. We apply that limit q naught should be tending to 0, since the charge q naught has to be very small. The reason being that if this charge q naught is quite big, then its own field will be bigger than this charge q, and it will affect the force that is experienced by it. So therefore, to understand it, we take a small positive test charge. Now this test charge, it experiences a force due to this, and hence in this way we can find out the electric field at this point. As we know from the Coulomb's law that the force between the two charges is given by F equals to 1 over 4 pi epsilon naught q over r squared, where r is the distance between the two charges. So if we use this, so it's 1 over 4 pi epsilon naught q naught over r squared, product of the two charges divided by the square of the distance. Now if we use this, we get the value of the electric field E to be equal to, this is the electric field due to a point charge, will be obtained as 1 over 4 pi epsilon naught q over r squared. Now we see here that electric field, it is a function of position. So we write ER, the electric field as a function of position, can be written as the constant 1 by 4 pi epsilon naught q over r squared. The same can be written in the vectorial form. So this is magnitude, and in vectorial form the same can be written over here with unit vector r cap. This represents the electric field at a point due to a single charge. In the same way, we can find out the electric field due to a number of charges. So here, now we take few other charges. We take here charge q1, another charge q2, another charge q3. We have these charges. Let this charge be q1, q2, q3, and suppose we want to find out the electric field at a certain point P. So at this point P, we want to determine the electric field. So the electric field at this point P can be obtained by finding the electric fields due to the individual points and adding them vectorially. So we obtain the electric field due to this charge q1 by joining this to the point P. So the electric field due to the charge q1, it will be along r. So this is electric field due to 1, which we write here as E1. Similarly, we can write the electric field due to Q2 by joining this point P to Q2. Electric field is again in the direction of R. So we write here E2. The third electric field due to E3 can be obtained over here by joining E3 to the point P. And again E3 can be written here. So we have E3. In the same way, whatever charges are there, we can obtain their individual electric fields at this point P, and therefore the net electric field at the point P will be given as E net to be equals to E1 plus E2 plus E3, all added vectorially. So we have E1, E2 and E3 to be added vectorially to give us the net electrostatic field at this point P. Once we obtain the net electric field at the point P, then we can find out the force experienced by any charge which is placed at this point. So we will just use that E net at this point should be equals to F over Q naught, and therefore if you want to find the force experienced at this point P, the force experienced F will be equals to Q naught times of E, which is the net electric field at this point. Now we'll do an example and find out the electric field due to a number of charges at a given point. So see, 2 point charges q1 and q2 of magnitude plus 10 into 10 to the power minus 8 coulomb and minus 10 to the power minus 8 coulomb respectively are placed 0.1 meter apart. Calculate the electric fields at points A, B and C as shown in the figure. So here in figure you can see we have the charges A, B and C, and we want to determine the electric field at these points. So we want the electric field at this point A, we want the electric field at this point B and electric field at this point C. We have these two charges Q1 and Q2. This question is from NCERT example. The distance between the two charges Q1 and Q2 is given as 0.1 meter. The charge Q1 is given to us as 10 to the power, this is positive 10 to the power, this is positive 10 to the power negative 8, and this is negative 10 to the power negative 8 coulomb. So first of all we determine the electric field at the point A, then we will determine the electric field at point B. To understand the electric field at the point A, we find out the electric field due to the charge Q1 at this point A. We find the electric field due to the charge Q2 at the point A, and then we can find the net electric field. Since the charge Q1 is positively charged, so its electric field, it will be radially outward. So at this point it will be in the direction of R. So joining Q1 to A, that is R, so it will be like this. This will be the electric field due to 1. We represent it as E1 at this point. Similarly, we can find the electric field due to the charge Q2. Since Q2 here is a negative charge, so its electric field will be inwards, and hence we can write the electric field E2 also along the same direction. It will be inward, so this is E2. The electric fields E1 and E2, They are acting along the same direction at point A. Therefore, the net electric field at this point A, we can obtain E net to be equal to E1 plus E2. That's the net electric field at this point A. The electric field at E1 will be given as 1 over 4 pi epsilon Q, that is charge 10 to the power minus 8, divided by r square, the distance from here to here, which is 0.05. So it's 0.05 squared. As the charge Q2 is also same, minus 10 into 10 to the, minus 10 to the power negative 8. So the magnitudes of E1 and E2, they are same and their directions are also same. We'll just evaluate E1 and hence we can obtain E net to be equals to 2 times of E1 or 2 times of E2, as E1 and E2 are equal to each other. Evaluating E1, we get 9 into 10 to the power 9, that's the constant, times 10 to the power minus 8, divided by 0.05 squared. So it's 25 times 10 to the power negative 4. This we get 9 over 25 times 10 to the power 5. So we can simplify this, 90 over 25 times 10 to the power 4. So 90 over 25, it gets cancelled with 5. 5 5s are 25 and 5 18 times. Now you can cancel this and you obtain the net electric field. So it is 3.6 into 10 to the power 4 Newton per Coulomb. In the same way, we'll find out the electric field at the point C. So see, to find out the net electric field at point C, we observe the electric fields due to the individual charges, electric field due to the charge at 1 and the electric field due to the charge at 2. So we obtain E1 and E2. At this point C, we want to find out the electric field. That point C, it is at a distance of 0.1 meter from Q1, it is at a distance of 0.1 meter from Q2, and therefore it lies in the midline of both of them. So to obtain this, again, either we can use the parallelogram law or we can use the resolution of the vectors also. Since the electric field at the point C, E1C and E2C, they are equal to each other as their distances are also equal and the charges are also equal. So here also we will have our electric field E1 to be equal to E2. The magnitudes of both of them will be equal to each other. So one way we can do, we will find out the electric field due to E1, which is in the radially outward direction as represented here by E1C. The electric field due to the charge 2, it will be inwards towards the charge Q2 and this is represented by E2C. So we will explore this. We will resolve E1C into two components. So we get here E1C and here also we'll get a component of E1C. Consider this angle to be theta. Since it's an isosceles triangle, so this angle would also be theta. So therefore we get these angles as theta and theta. So both the angles are theta. I break E1 into two components. Here I get E1C cos theta and here I get E1C sin theta. Breaking down E2C into its components. So I'll be getting here E2C cos theta and along the vertical in the downward direction I will get E2C sin theta. Since the magnitude of E1C and E2C, they are same, so the y components, they cancel out each other. The two components, their magnitudes are same. E1C sin theta and E2C sin theta, their magnitudes are same, so they cancel out each other and you have the resultant along the x-axis only. So the net electric field over here will get E net. We can write it as 2 times of E1C cos theta. So This would be 2 times of E1C. E1 can be obtained by the formula K, that is 9 into 10 to the power 9, divided by R squared times of Q. So Q, either charge we can write 10 to the power minus 8. The distance R is 0.1, so we put here 0.1 squared. So this is 0.1 squared K Q over R squared. Now you have cos theta, so we write here cos theta. This value you obtain here 18 into 10 to the power 1 divided by 0.1 square, so it's 0.01 times cos theta, and cos theta is base over hypotenuse, so it's 0.05 divided by 0.1. So we get again 90 into 10 to the power 2. So the net electric field at this point would be 9 into 10 to the power 3 Newton per Coulomb. Let's move to the next problem and see what can be. So now you have two balls, two small balls having equal positive charge Q Coulomb on each are suspended by two insulating strings of equal length L meter from a hook fixed to a stand. The whole setup is taken in a satellite into space where there is no gravity. Then the angle theta between the two strings is. So you have two small balls having equal positive charges Q on each other separated by insulating strings. So we have one string over here, we have another one, we have the two spheres such that they are separated by some distance. Now each of them carry a charge Q. So when on earth, they both will be inclined at a certain angle. The net force that will be there here, each of the charge will experience two forces. So the first charge, if I draw either of them, let's see on the first charge over here, if I see, there are two forces which are acting. So you have the downward weight mg and you have the electrostatic force of repulsion. So therefore, it will experience a net electrostatic force uh, according to the parallelogram law in the diagonal direction, and hence the two will repel each other and it will be shifted by a certain angle. Now the situation is we are not including this gravity. There is no gravitational force acting on the two charges. There is only electrostatic force of repulsion between them. So when there is only electrostatic force of repulsion between them, since the two forces they are acting opposite to each other and they are tied to a hook, so therefore there will be a linear motion towards opposite to each other. The two of the charges they will move opposite to each other, and hence they will move in a situation where they will have the minimum repulsion. So to have the minimum repulsion, they will be aligned like this, opposite to each other. So one of the charge you will find over here and the other charge you will find over here. This is the situation when they are having the maximum distance between them, and hence the minimum force of repulsion will be there, and therefore the correct answer for this will be theta equals to 180 degree. So remember that there is no gravity acting on them. So this is C, 180 degree. Next we see two charges 4q and q are placed 30 centimeter apart. At what point the value of electric field will be 0? So we again draw the two charges. We have their charge plus 4q. We have another charge here which is q. This is 4q charge q, they are separated by a distance of 30 centimeter. Now we want to find out a point where the net electric field due to them will be 0. So we try to see where all the electric field can be 0, as the two charges, they are of the similar nature, they are either positive or negative. So considering them to be a positive, you can consider either negative, the result will remain the same. So the electric fields due to each of them will be outward. The electric field due to this one will be outward like this in all the directions. The electric field due to this will also be outward like this. Since on this line, if we observe, the two electric fields, they are opposite to each other on the line joining the two charges. So there must be a point P where the electric field due to both of them must be 0. So we try to find out this point. Suppose this point is situated at a distance x from this charge 4q. This is x centimeter from this charge 4q. So we'll find out the force at this point. The electric field at this point, net electric field at this point due to the individual charges, and add them to be getting them equals to 0. So we obtain electric field due to charge 1, we call it as charge 1, this one as charge 2. So electric field at this point P due to the charge 1, we can write it as K times of Q, which is 4Q divided by the distance x squared. The electric field due to the charge Q2 will be E2, which will be represented as K times of Q over 30 minus x. Now, the difference of the two electric fields should be equal to each other, should be 0. So we write here E equals to 0. Therefore, we must have E1 equals to E2, or E1 minus E2 equals to 0. So if I put both of them equal, we get K times of 4Q over x squared to be equals to K times of Q over 30 minus x whole square. Now, from both sides, K cancels up, Q cancels up. We can solve this by taking the root on both sides. We get 2 over x to be equals to 1 over 30 minus x. We get 60 minus 2x to be equals to x. 60 equals to 3x, and hence we get x equals to 20 centimeter. So now this is 20 centimeter from the charge 4q. So from the charge small q, or from the charge q, the distance would be 10 centimeter. So the correct option is 10 centimeter away from the charge q between the charges. So this is correct option A. Now I move to the next question. Two identical point charges are placed at a separation of L. So we have two identical charges. Here, let this be charge Q, this charge Q. They are separated by a distance L. P is a point on the line joining the two charges at a distance x from any charge. So you get here a point P which is at a distance x from any charge. The field at P is E. So we are marking a point P over here. This is at a distance x from this first charge. The electric field at this point P is represented as E. E is plotted against x for the values of x from close to 0 to slightly less than L. Which of the following best represents the resulting curve? So you have to start the value of x from 0 to up pretty close to L. So if I start from 0, so from here, this is our x, we are starting this x from 0 up to L. So as if I'm closer to this charge, the electric field will be E. At this point, the electric field is E, and as I move away from it, the electric field decreases, since we can write the electric field at a point to be equals to varying inversely as r squared. So the electric field at this point or on this line it will vary inversely as r squared, and at a point exactly in between the two, the electric field would be zero. Since the electric field due to this charge will be in the outward direction, the electric field due to this will be in the outward direction. The two electric fields, they cancel out each other. The net electric field at that point would be zero. Now, as we move from here a little bit more ahead and ahead, the direction of the electric field changes. So on this side of this neutral point, you have the electric field, which is on this point. You have the direction of the electric field, which is on one side. On the other side, you have the electric field, which is opposite in the direction. So if you observe these points, what we observe, first of all, we obtain that electric field, it varies inversely as r squared. Then second point, we observe that here that electric field, it becomes zero and then it changes its direction. So the correct graph which represents this can be shown by the graph D. The first graph, it shows electric field to be decreasing, becoming zero, and then again increasing in the same direction, which is not happening here. The second graph, it shows decreasing, but this is not according to the inverse relation. The third graph, it doesn't show inverse relation. It shows that it's constant and then decreasing. So this is not an inverse relation. So C is not correct. This last graph, it shows electric field to be decreasing inversely as r squared, becoming zero and then increasing in the opposite direction. So correct answer is D. Thank you everyone. We'll meet again in next class to find out the electric field due to continuous charge distribution. Thank you.